All right. Today we are going to get into probably the most unpleasant of the tests, not because the test in and of itself is difficult, okay? The test, like the concept behind the test is fairly simple, the integral test here, but this is definitely, out of all of the tests that we're going to look at in this section, this is the last one in line. This is the one that I don't want to have to use if I don't have to. It requires, in my opinion, it requires probably some of the largest amount of work. It obviously is going to incorporate an integral somehow. With that said, this test is being taught at this stage because without this test, all of the other tests kind of become null and void. We can't really prove these other tests without looking at the integral test. We won't be able to talk about p-series unless we talk about integral test. We won't be able to use comparison tests until we know what a p-series test. The only other ones that exist are a ratio test, which is cool, and we like that, and we'll make sense of that when we get there, and that's really the only other one that isn't going to use this integral test. So, the concept behind the integral test is it's a test that it's very powerful. It is going to work on any series that we have. All right? Just because it works doesn't mean that it's going to necessarily be easy. But conceptually, it's pretty straightforward. It works a little bit like this. If I have some sort of series, and if that series produces terms in such a way that I'm going to have some a of k that's going to equal some, and I give you this other a of k. The concept is I want to basically have a of k have a relationship. I want that to relate to some f of x. Okay? Where a of k and f of x, as long as the x is a positive number, so x would be 1, 2, 3, 4, 5, and k is 1, 2, 3, 4, 5. If that x and k kind of line up with each other, I want those to be equivalent values. However, a series has positive integer values. By the way, for those of you who have never seen this before, we call that z plus. Okay? Yeah, integers are z. Those of you who are interested in possibly majoring in mathematics get to know that symbol well. All right? But all that means, integer values for the domain versus f of x, and f of x is going to have positive real number domains. By the way, for those of you who don't know what reals are, it's the creepy looking R. And you should have seen that one at least. Right? Good. So the idea is that these two are related to each other, but are they the same thing? What do you think? Is having positive integer values for the domain the same thing as having real numbers for a domain? And the question really becomes, if I look to graphs, does this give me the same thing as this? The answer should hopefully be no. Okay? All right. Cool. So here's what it does. Let's say we come up with a function that relates, and I look at that f of x function, I realize that f of x function is three things. It must be continuous. If the function is not continuous, we cannot take the definite integral of it, and then we have some sort of failed at life type moment, okay? So we have to have a continuous function. We have to have a positive function. All values must be greater than 0 for this to work, and the function must always be decreasing. And if that f of x is always continuous, positive, and decreasing for the x values we're looking at, then that function's integral from 1 to infinity will do one of two things. That will either converge to a value or it will diverge to infinity. If the function winds up diverging to infinity, then that tells me that the series also diverges. And if the integral converges, then that means my series will also converge. So let's take a look at that real quick. Looks something like this. We have the integral n is equal to 1 to infinity of 1 over 3n plus 4. Okay? When I look at the series 1 over 3n plus 4, I want to basically come up with a function that would match that. It's really easy, folks. The function that matches the series 1 over 3n plus 4 is the function 1 over 3 x plus 4. And my question for you is when the x is greater than or equal to 1, as you can see, n starts at 1, so we're going to let x start at 1. When x is greater than or equal to 1, can you say this function is continuous? Do you agree with that? Is it positive? Is it decreasing? Well, how do you know if it's decreasing? Yeah, bottom keeps getting larger, top stays the same. It's got to be continuous, positive, and decreasing. So far, so good? Since we know that that 1 over 3x plus 4 when x is greater than or equal to 1 is continuous, positive, and decreasing, this is a problem that qualifies for the integral test. So now we use the integral test to attack this. We say, well, if this is the case, let's take the integral from 1 to infinity of 1 over 3x plus 4 dx. And my question to you, should that integral converge or diverge? What do you think? You think it's going to converge? Let's find out. By the way, I do want to make a point. I didn't mention this before I started the work. Before I do an integral test, there's one test I'm always going to do very quickly. Anybody care to guess which one I'm going to do quickly? I'm going to do an nth term test on this, because the nth term test is stupidly easy, right? Nth term test. Let n go to infinity. What does that equal? You sure? 1 over 3n plus 4? If n goes to infinity, what do we get? 0. So what do we know about nth term test? That failed completely. Because it's the nth term test for divergence. If the test fails, it tells us nothing. We need nth term test to be something that's not 0. So if terms go to 0, let's see what happens here. We cannot take the integral from 1 to infinity. We can only do a limit. So I'm going to rewrite this as the limit as b approaches infinity from 1 to b of 1 over 3x plus 4 dx. Wait, this is starting to look a lot like that improper integral stuff. Of course it is. It's an improper integral. All right, so my question to you then, what's the antiderivative of 1 over 3x plus 4? It is a natural log. In fact, it's going to be 1/3 the natural log of 3x plus 4. Notice that I'm not worrying to put the absolute value on. Why am I not worrying about that? I've already said that it's positive, so why the heck do I need to turn the numbers into positives? What? Math making sense? Take that stuff out of here. We don't believe in that. Okay, I need to evaluate this, so what I'm going to do, I'm going to use that fact that constants can be pulled outside of the limit, 1/3 the limit, as b approaches infinity, of the natural log of 3b plus 4 minus the natural log of 7. What do I get? Whoa, wait a minute. So the term's turned into a 0, but it's still diverged. Oh, dang it. This diverges. Since 1 over 3x plus 4 is continuous, positive, and decreasing when x is greater than or equal to 1, and the integral that goes from 1 to infinity of 1 over 3x plus 4 dx diverges, we can make a final statement that the series diverges by integral test. Quick aside, unlike any other portion of the calculus test, you have to name what test you are using when you make your final conclusion. Remember that it wasn't necessary for you to say that you used IVT as long as you stated all the conditions, right? Technically, you didn't have to state NVT unless you stated all the conditions. Now, is it nice to be able to state that? Sure, it's nice to know that it has a name. But when you're doing these tests, you want to be very, very clear that not only have you reached the conditions, but also showing them that I know that this test is really this one. All right? And they will want to see that as you go through the problems. I've stated all the conditions: continuous, positive, decreasing when this is greater than 1. When x is greater than or equal to 1 of that function, I showed my limit, I evaluated it, showed that diverges, series diverges, done. It's the same process no matter what we do. Okay? So for instance, if I look at B, I look at that and I say, well, there's a series. I can see I'm going to add up an infinite number of terms of 1 over n cubed. I'm thinking to myself, what would be a nice test to use? Nth term test would be a great test to use. I use the nth term test, and then I weep a little bit because that converges to 0, and I didn't want it to converge to 0 because now the nth term test failed. Darn it, I hate that nth term test. It doesn't seem to do anything anymore. Don't forget the nth term test. It will do things. Just doesn't always do things, otherwise we wouldn't need any of these other tests, which would have made life a whole lot easier. Really, it just shows you that mathematics is broken. Okay, so 1 over n cubed is really looking at 1 over x cubed, and we're going to look at that when x is greater than or equal to 1, because the n starts at 1, and we know that that is it positive? Or is it's continuous? Yeah, let's start with continuous. That's always a good thing to start with. It's continuous. Definitely positive. And decreasing. So 1 over x cubed when x is greater than or equal to 1 is continuous, positive, and decreasing, which means we can use the integral test. The integral from 1 to infinity of 1 over x cubed dx. Yes, you do need to use x. You are not allowed to use n because n has already been defined as in positive integers. You have to use x because it will be identified as positive real numbers. Again, we cannot do this just as written. We have to do the limit. And yes, they are looking for that. And I'm going to rewrite 1 over x cubed as x to the negative 3 dx. And I just need to know what is the antiderivative of x to the negative 3. X to the negative 3. X to the negative 2 over negative 2, evaluated from 1 to b. I may choose to rewrite that because I really don't like the way that's written right now. I would probably call it negative 1 over 2x to the 2, evaluated from 1 to b. Is everybody good with that? All right. So let's go ahead and see what we can do. I'm going to factor out that negative 1/2, leaving me with just 1 over x squared. So I'm finding the limit as b approaches infinity of 1 over b squared minus 1 over 1 squared. What do I get? Heard it. It is 1/2. By the way, if I ever do one of these problems and I wind up with a negative value, I know I did something wrong. Why? Because if my x's are already, if my y values have to be positive, then how on earth did I get a negative integral, right? Okay, so we wind up getting that. We get 1/2, which means that this converges. Therefore, our series converges by integral test. Please note something that I did not write. I did not write that the series converges to 1/2 by the integral test. As a matter of fact, I know 100% for a fact that the series is most definitely not 1/2. In fact, if we look at the last question, the last example, it wants to know what is the smallest and largest value. It wants to know the low, actually it's not the smallest and largest value, it can be. It wants to know the lower and upper bound of what that series will equal. Ladies and gentlemen, for you to find that out, I provide for you some light reading. Ladies and gentlemen, if you will flip over the next 3 1/4 pages, are textbook readings of the integral test that will be, which contains how we would find the smallest and largest value that the series will equal. I will give you about 15 minutes, 15 to 20 minutes to read through that. You may discuss with each other as a group what that is. For the video, I will pause it, so after the pause, we'll just go back in so there's not 15 minutes of silence. All right? Very awkward silence. Not good, not bad. Okay, this is some really weird stuff. So let's go through each of the pages, kind of make sense of, let's find out what made sense and what didn't. So in this initial page, was that pretty good? Yes. Yeah, that was really what? Kind of getting you built up for the idea that the series is really just like a Riemann sum, right? Yes. So we built up, said that. We restated the integral test that says if the series converges, if and only if the integral converges. An interesting thing, so I don't know if you've talked about this in other classes, but if and only if is one of the most powerful statements we have in mathematics. If and only if says that if the series converges, then the integral converges, and if the integral converges, then the series converges. Okay? Now, example of something where if and only if doesn't work. It rains if and only if the ground is wet. Now, if it rains, is the ground wet? Absolutely. If the ground's wet, did it rain? Absolutely not. So if and only if, it's a really powerful logical thing. So to say that this leads to this, then this leads to this, we can prove it either way. All right? And then the corollary is a diverge statement, and then we get into all of this. So on this page, is there any spot that we started getting tripped up a little bit? So the concept here is that we're really only looking at the series starting at 2 to infinity, because if we're using a right-hand Riemann sum starting at 1, the right-hand Riemann sum is actually going to start at 2. So we begin talking about that. We say that the series started at 2 is less than the integral from 1 to infinity, or 1 to some n value. Agreed? They then proceed to explain, well, integrals from 1 to a finite value are definitely less than the integral from 1 to infinity, given that the function is positive, continuous, and decreasing, right? So then we can make that statement that the series at 2 is less than the series from 2 to a finite value is less than the series from, or the integral from 1 to infinity. So far, so good? The next one is where things get weird. Remember, in my theorem, I stated that the series from 1 to infinity is smaller than the integral from 1 to infinity, or is going to converge if this from 1 to infinity. So I have to prove, we are going to, so I have to, basically what I'm trying to do now is I'm trying to figure out, well, how big can this series actually get? So what I'm going to do is I'm going to assume that that converges. If this converges, then does that have to converge? Absolutely, because if that converges and this is smaller than that, then they both should meet the same value. So we get over here. Don't let the... Did anybody get creeped out by the weird M that just magically appeared on the paper? Welcome to M for Magic Math. Yeah. M just magically shows up. All that's saying is that that's a finite value, a constant. What winds up happening is to turn this into a k from 1 to n, we had to add an a of 1 to my summation. And if I add a of 1 to the summation here, I have to add an a of 1 to the summation to the integral here. Well, a finite convergent thing plus a constant, is that still convergent? Absolutely. Now what this tells us is actually something really, really useful. It tells me that my series is smaller than the first term plus the integral. You may want to write there. This line right here tells me my series is smaller than my first term plus the integral. They then proceed to talk about partial sums and how we're going to have an increasing partial sum, which makes sense. And that should converge. And if that converges, then of course we also know that by definition, if the partial sums converge, then the sequence converges. Yes, ma'am? Yes, sorry, thank you. The partial sum converges, then the series converges. Thank you. It's far too many words. On the second part, now they say, okay, now we want to create a situation where the series is greater than the integral. So now instead of a right-hand Riemann sum, we're going to do a left-hand Riemann sum. Notice that when we get to the nth term, we don't go to n, we go to n minus 1. Is everybody okay with that? Basically, we took the last problem where we went from 2 to n, and then we said, well, if we want to go to the left, we want to do 1 to n minus 1. So we did a left shift, which is why we go from 1 to n minus 1 here. And we do agree that this is bigger than the integral. Okay, now let's assume that the integral diverges. If the integral diverges, and this is bigger than the integral, then that means that my series must diverge, right? But what that does is it tells me that this integral down here, right here, since that goes to infinity, this piece right here tells me something else useful. Because if n goes to infinity, then this is really just 1 to infinity, and this is really just 1 to infinity, right? And what does that tell me? That tells me that the series has to be bigger than the integral. So wait, you might want to write that somewhere down here. The series is bigger than the integral. So wait, I just said that the series is bigger than the integral, but it's smaller than the first term plus the integral. Ladies and gentlemen, what does that mean? It means I know the bottom value, a lower boundary for the series, and I know a upper boundary for the series. Which takes me back to the very last question on this page. What this states, and it's actually up here on the top inside your theory spot, but what this states is that the integral from 1 to infinity of 1 over x cubed dx is smaller than my series, which is smaller than the first term plus the integral. Or, put another way, what did the integral equal? The integral was 1/2 is definitely less than what my series is. And that is definitely smaller than, what's that 1/2? What is the first term for this? A of 1 would be 1 plus 1/2. Ladies and gentlemen, have a fantastic day. I promise to you that you do have an assignment. It is that very large integral test. This is the big assignment, folks. This is the tough one. There's a lot of work. It takes up quite a bit of space. Make sure to get it done tonight. I promise that tomorrow is the easy day. And I don't even mean that facetiously. So have a good one, folks.